In physics, we come across different type of waves: sound waves, electromagnetic waves, matter waves in quantum mechanics, and water waves. Now, mathematically, the wave equation is represented like this. And here we can see two different signs, one plus and one minus. Now, what does this sign really means? And what really decides whether a wave is moving towards left or right? And why do we need two different expressions, one with plus and other one with minus? All these questions we are going to address in this video. First, let us try to understand what we mean by phase. Let us take a simple pendulum. Now, in this simple pendulum, let us displace this mass towards the right hand side, and we will call this position or this configuration as A. Now, this pendulum will go towards the extreme right, and it will try to come back towards the mean position. So this we'll call it set B. And now this pendulum will come at the mean position and it will go towards the left hand side. Notice the difference between A and B. A and C. Here A and C, the position are the same, but the pattern of the motion is different. Now again, after C, it will go back to the extreme left position and it will try to come back, and we will call that configuration as a D. And finally, it will come back at the mean position and again it will try to go towards the right hand side, which is same as A. Now, this A, B, C, D, A are different state of motion of this oscillation. So, in oscillation, the phase determines the state of motion. What is phase of a wave? The phase of a wave tells us what the wave is doing at a specific location and moment, whether it is at a crest or trough or somewhere in between. So basically this depends on the position and time. Here I am denoting the phase by phi, and it is a function of x and t. Now, the general expression of a wave will be a function of x and t, and we can assign a maximum amplitude A, and it will be a harmonic function of the phase. Now, this phase, it will consist of a space part and a time part. The space part we denote it by kx, and the time part we denote it by omega t. Let us take an example of a system where we have an array of particles connected by string, and this string allows bending. So if I disturb the particle number 1, and because of this disturbance, the particle number 2 also will be disturbed. And as time goes on, the disturbance will be transferred to the nearby particle. Now just try to observe the front portion of the disturbance. They are all the same and they are propagating towards the right hand side. So the particle oscillation leads to the transfer of motion to the nearby particles, and this leads to the propagation of the wave. And as the wave propagates, it carries the shape through space as time goes on. And from this example, we can see that the shape is the same as the wave propagates. And the shape of this wave is related to the state of motion. And state of motion is basically the phase. So when the wave is propagating, the phase is constant. On the right hand side, I am showing an animation where the vertical oscillation of the particles leads to the propagation of the waves. Now let us discuss this constant phase condition. So we have the mathematical expression of the wave. So the phi, the phase, can be expressed as a combination of space and time part. And since the phase has to be constant, so we'll denote phi is equal to c, some constant. And here k and omega are constant parameters. Now, as time increases, this omega t factor will be a positive quantity. So let us see what happens to the two expression, one with plus and the other one with minus. So let's take the plus one first, that is kx plus omega t. So as time increases, the omega t factor will increase. But the phase has to be constant. So since the phase has to be constant, the other term kx has to decrease. Because when one is increasing, the other one has to decrease in order to negate and give a constant phase. So that means here k is positive, so x has to be negative. So the wave will be a left moving wave. Now let us take another expression, kx minus omega t. So omega t will be decreasing because there is a negative sign in front. So the kx has to increase, and k is positive, so x has to be positive. So it is a right moving wave. Let us take another example. Let's say the wave equation is given like this. So let's take out the phase part, and it has to be constant, so I'm denoting it by c. So this minus kx plus omega t. So as time goes, the omega t factor will be increasing. So this minus kx has to decrease. So since minus is already there and k is positive, so x has to be positive. So it's a right moving wave. Till now, whatever we have discussed, we were focused on wave traveling in 1D. So now let us generalize that concept to 3D. So in 3D space, the k will be replaced by k vector and x will be replaced by the position vector. And the product, that is kx, will be replaced by the dot product of the k vector and the position vector. So the wave equation will look like this. Now the phase part in this expression is this one, the dot product of k and r minus omega t. And we have to take this phi to be constant. So in this case, what will be the direction of the wave? Now, let us find out the direction in 3D. So we have the phase expression, which is constant, and so I'll rearrange and denote the constant by phi naught. So at a particular time t1, at a given time t1, the dot product we can write it as a constant c1 because t1 is given and the other parameter are constant. So we can write the dot product of k and r, it's a c1. Now remember, k is a constant vector. So if I divided on both sides by the magnitude of k, then you can write c1 by the magnitude of k as c2. So this is the final expression. That is the dot product of the unit vector of k and the position vector. Now, what does this equation represents? It's very interesting. Now, let us take an origin O, and let's say the constant vector k is in this direction. Now, if I take a point P, which is at R from the origin, then if I take the dot product with k vector, then this represents the projection of R along the direction of k. Now this dot product is a constant. Now if I try to find a similar type of points which satisfies this condition, that is k cap dot R vector is equal to c2, then I'll be getting a plane. So basically this equation is a equation of a plane. Now this plane was calculated for a particular time t1. So in another time t2 we'll have a different constant, and that will also give a plane. So the plane of constant phase is perpendicular to k, and as time goes on the plane shifts parallel to themselves, And this shifting of plane is basically the propagation of the wave, which is along the k direction. So in summary, in 3 dimension, the wave does not just travel like a ripple or a string. Instead, it moves through space as a series of plane of constant phase. Thank you everyone for watching this video.